Okay, so good morning. So let's get started. So what we're going to do today is, I guess I will speak a fair amount of time, 1 hour or so, continuing this memory management basics. And today I'd like to go into this Rust memory management stuff, which is, I guess, the most complicated part of this entire course. And still, you have some time to work on this assignment, PL05 calculator, so as a group. And I released another notebook. I don't think we can get into this exact topic for today, but well, just so that if you have already finished this PL05, I released the next assignment. And this one is also going to be assignment you are going to submit through ITCLMS. So it's going to become the second assignment. And you already should have another folder in the same OneDrive folder I gave to you for this previous assignment. So currently ongoing assignment. So please make sure you find this assignment 2 folder in which you work on this PL05, PL06, the next one. And until the time you start working on this assignment today, make sure that you indicate where you are in this Google Sheet. So some of you are already doing this. But okay, so I will check this again just before we start this group work. Okay, so can I get started? Okay, so this is a topic we have just going through in the last week. And most important recap is presumably this slide. So memory management is complicated. So the fundamental reason why it could go wrong is, so when you reference a pointer in the C's terminology, but something like pointers exist in other languages too, right? So when you are using Python, Java, or whatever languages, so you have a reference to an object, right? And you occasionally like to dereference it, right? So dereference meaning reference a field of it, or reference an element of an array or something like that. But if the data structure, it has already, and the data structure itself has already gone, or the first memory block has already been reclaimed, then you get into trouble, right? So the fundamental way the memory management could go wrong is this, right? So you have a reference, you want to dereference, but the data structure, it is supposed to be pointed by the reference, may have already gone, right? So this is exactly what we make sure never happened in your language. And to this end, well, there are many, not too many, but there are several ways to make that never happen. So one is garbage collection. So the basic way the garbage collection works is simply you assume that objects or memory blocks may be used in future if there's a chain of references from the root to that particular memory block, right? So these arrows represent a reference, or pointers in C's terminology, but reference in other languages. And the root is either local variables of currently ongoing function calls, so currently active function calls, or global variables. These are root. and those objects that can be reachable from the root by traversing one or more pointers or references are assumed to be used in future. So this is basically how the GC works. And I introduced several terminologies on what is an object and what is a root, reachable objects, live or dead objects, garbage collector, mutator. But in the shortest terms, the basic principle of garbage collection, the basic way the garbage collection works is that it assumes, well, not necessarily it assumes. So the basic principle is that objects unreachable from the root are dead. They can be safely reclaimed. There's no way that the program still uses these objects. If there's no way from the root, you can reach these objects, right? So this is the basic principle of garbage collection. And speaking about the garbage collection, actually, well, it is further classified into two broad categories. One is something called traversing garbage collection, and the other is something called the reference counting garbage collection. So garbage collection is usually abbreviated as GC, and the reference counting is usually abbreviated as RC. And some people distinguish between reference counting from garbage collection as if they are totally different things. And some people do not call reference counting a part of the garbage collection, but the exact details of the terminologies do not matter. So in this slide, I call all these two, traversing or reference counting, both as a subcategory of garbage collection. Well, the details, so terminology details do not matter very much. So for traversing garbage collection, so it simply traverses pointers from the root, so literally to find all objects reachable from the root by traversing pointers, and reclaims objects that are not visited. So this is as simple as this. And this traversing garbage collection is further classified into two broad categories. I do not get into them today, but in later weeks. So one category is something called mark and sweep garbage collection, and the other is copying garbage collection. And the other category I call the reference counting. So it works by maintaining something called the reference counts, which is the number of pointers pointing to a particular object. So each object has a reference counter. And we maintain the reference counter during the execution. And it reclaims an object when its reference count drops to 0. So it happens immediately when its reference count drops to 0. So one small note about the connection between this reference counting and what I have been talking about earlier is that obviously, if an object reference count becomes 0, then it's unreachable from the root, right? So there's no pointers referencing to it, right? So there's no way you can reach that object from the root, right? So these are two broad categories. And I briefly talk about each of them in this slide, and hopefully get into the last. And I come back to more details about garbage collection in later weeks. Okay, so briefly about two garbage collections. Okay. So this is how traversing garbage collector works. So just like I said in the last slide, well, it literally works by finding all the reachable objects from the root. It does so by simply traversing all pointers from the root. So like this. So this is the root. So either global variables or local variables of active functions. And starting from the root, it traverses all the pointers in the root, just like this, and mark these objects as have been visited, right? So these are obviously a part of the reachable objects, right? But these are not only the reachable objects, right? Obviously. So these objects pointed to by one of these reachable objects are also reachable. So we mark them accordingly. So we keep doing this until we do not find any more reachable objects that have not been visited already. So actually the traversing stops here, right? So there's no more pointers from these orange or red objects pointing to not already orange or red objects, right? So the traversing stops here, and these white objects are identified as garbage or reclaimable, unreachable, or whatever. So this is how reference counting works. So the other one, right? So like I said, each object has a number called the reference count. So these are reference counts of each object. And the reference count of an object is the number of pointers pointing to it, right? So this object has a reference count of 1 because there's one and only one pointer pointing to it. But for example, this object has a reference count of 2. So there are 2 pointers, right? And importantly, so we maintain or update reference counts during the execution. So there are many situations, there are many circumstances during the program at which reference counts will change. But they are basically some form of assignments. So values passing from one variable to another. So let's consider what needs to happen when we execute an assignment statement like this, P equal Q. So what needs to happen here is that, okay, so what happens here is that an object that is referenced by this Q variable will now become referenced by P also, right? So after this assignment. So P and Q, so both variables, P and Q, now point to the object that has previously been pointed by Q, right? So what needs to happen in terms of the reference counts is that the reference count of the object P previously pointed to should be decreased by 1, right? So if P used to point to another object, after this assignment, this reference has gone, right? So the reference count of the object pointed by P should now decrease by 1. On the other hand, the reference count of the object pointed by Q should be increased by 1 after this assignment, right? So these 2 things must happen. But this way you can imagine that you can maintain the reference count of each object during the execution, albeit some overhead, right? So let's say one of the objects' reference count becomes 0 as a result of a statement like this. Then, okay, let's say this happens on this object. Then reference counts of objects pointed to by this object now decreased by 1 too, right? So first of all, so if the reference count drops to 0, for this object can now be reclaimed, right? So this object should be gone. But in addition to just reclaiming this object, the reference count of objects pointed to by now gone objects should be decreased by 1, right? And as a result, the reference count of those objects may drop to 0 too, right? So this continues. So these two objects can now safely be reclaimed. And as a result, the reference count of this object is decreased and drops to 0. And this guy is also reclaimed. So nothing more happens. So after, okay, so the hypothetical assignment which drops to the reference count of this object 0 to 0, then yeah, this is the end state. So, well, this example was actually intentionally made to contrast the traversing garbage collection and reference counting. So the object graph I was using was exactly the same. So in the case of traversing garbage collection, only retained objects are these 5 objects. But on the other hand, in the case of reference counting, well, actually, these objects are not reachable from the root, but they are still retained. So all of these objects have a reference count, non-zero reference counts, but they are yet unreachable, right? So there is a subtle difference between reference counting and traversing garbage collection. So in other words, so an object's reference counts becoming 0 is a sufficient condition for the object to be safely reclaimed, right? So it is a sufficient condition for object to be unreachable from the root. But there are actually objects unreachable from the root whose reference counts are not necessarily 0. So this means that the reference counting may not be able to collect all the unreachable objects that could be reclaimed by traversing garbage collection. So this makes an interesting trade-off between traversing garbage collection and reference counting. Okay, so like I just mentioned, so these objects are unreachable from the root, yet cannot be reclaimed by reference counting. So I have already briefly talked about this, but somewhat more details about when different RC changes. So when the reference count changes, basically whenever a pointer variable gets updated, like p equal q or p arrow f equal q or something like that, or a function gets called. For example, when you have a pointer pointing to an object and you are passing this pointer to another function. So you are essentially making another variable pointing to the same object, right? So the other variable is the parameter of this function, right? And another circumstance in which reference count changes is when a variable goes out of scope or a function returns. For example, you have a variable scoped in this block here, right? But this variable cannot be used outside this scope, right? So basically, the RC of the object pointed by this variable should decrease at the end of this block, right? So basically, whenever any, so at any point, a pointer variable gets copied or becomes no longer used, a reference count changes. Okay, so I will cover more details about garbage collection in later weeks. So this is a very brief introduction that is necessary and hopefully useful before I get into how Rust works. Okay, so is there any question at this point? Okay, so let me go into Rust. So I'll be speaking about Rust memory management. And I don't think I can finish the entire slide for today, but so I'm going to speak until something like 11:25, so that you have some time to work on the assignment and the exercise during the class. So just as a heads up, so the topic is somewhat complicated, but so Rust is known as a language that is safely managing memory without garbage collection. So this is a very interesting topic in its own right. So garbage collection is, at least conceptually, very straightforward, right? So the way the memory management goes wrong is when you reference up, when you try to dereference a reference or pointer, when the object it points to is already gone, right? So this is, well, no matter how you do that, so this is what you like to prevent from happening, right? And the garbage collector works simply by making sure we retain all objects that may be reached by referencing pointers, right? But it takes some cost. So these costs are covered by later weeks, but this is not free either when you use traversing or reference counting. So it is natural to try to do something. Well, I'm not sure whether I should say it's better or not, but well, at least it makes sense to try to do it differently other than garbage collection. So these are yeah, somewhat complicated topics I'm going through, but let's move on. So this is the overview. So the very basic idea to memory management in Rust. So Rust maintains that for any live object, there's one, so exactly one and only one pointer that owns it. So it is called the owner pointer or owning pointer. So basically, there's only one, exactly one pointer that determines the lifetime of the object. So this is called the owner pointer. And in addition to owner pointer, besides the owning pointer, there can be any number of something called borrowing pointers or references. So non-owning pointers. It doesn't matter very much how many. So, but you can have any number of borrowing pointers pointing to an object. But the important point is that they cannot be dereferenced after the owning pointer goes away. So this is the rule enforced by the Rust memory management. So if these two rules are somehow enforced and guaranteed, then Rust can safely reclaim the data when the owning pointer goes away, right? So this can be illustrated like this. So for any object or memory block, there's one pointer pointing to it. And there may be multiple or any number of borrowing pointers. But we somehow, I haven't talked about how exactly, but somehow we guarantee that these borrowing pointers are not dereferenced after the owning pointer goes away. So then it is safe to reclaim this data at the right time the owning pointer goes away. So at the same time, the owning pointer goes away. So basically what the last does is somehow maintain or identify what is the owning pointer to each object and reclaim each object when its owning pointer goes away. And make sure that other pointers, borrowing pointers, are not dereferenced when the object's owning pointer goes away. So this is the basic idea. So I just named it a single owner, multiple borrowers rule, or just to make it easy to remember the underlying concept. Well, it's not very important that there may be multiple borrowers. So the important thing is borrowing pointers cannot be dereferenced after the owning pointer goes away. Therefore, the object itself goes away. So this is the most important and the basic idea. So just to make sure. So if you have any question at this point, so please ask. Yeah, is it clear so far? And the one more important thing is, so probably you have already been aware of this, is that these rules are enforced statically, not dynamically. So the last maintain the rule statically. So in other words, it enforces or it checks if these rules are obeyed by your program at compile time. So rather than at runtime. Or yet another way to put it is it checks if these rules are obeyed before the execution of the program, not during the execution. So this is a slightly aside, but there are actually ways outside these basics. So these two things, so owning pointers and multiple borrowing pointers, these are the backbone of the Rust memory management. And this imposes certain restrictions on the way your program can be written. I'll get into some of them later. But these are actually pretty restrictive in cases. So for those cases, in which the program cannot be conveniently written obeying these restrictions, there are some ways outside these basics. So there are some ways you can get around these basics to be sure. So one way the last allows you to get around these basics is reference counting. So this is exactly what I have mentioned in earlier slides. So in other words, it allows you to have multiple owning pointers. So there may be some number of owning pointers, and when all these pointers are gone, the object itself will be gone. So these are reference counting. So Rust provides reference counting. And yet another way that the Rust allows you to get around these restrictions is something called unsafe or raw pointers. So these are just like C pointers. So whose safeties are totally up to you. So the Rust doesn't guarantee anything in particular. So these were provided just in case your programs cannot be otherwise written. But these are arguably not interesting part of the Rust memory management. So I'm not going to cover them in the rest of this slide deck. So in the rest of the slide, I'm almost totally focused on how these basic rules, so single owning pointer and multiple borrowing pointer works. Well, just to be sure, so there are some ways around them, but these are not specific to Rust language, and these are not central part of the Rust memory management scheme. So let me make the concept I have mentioned more specific in the context of Rust programs. So there are several pointer-like data types in Rust. So let's say you have a type T. It may be just a 32-bit integer or struct or enum. So given a type T, the following are types representing references or pointers to type T. So there are some multiple ways you can make something like a pointer to a data structure. So the simplest is something called ref_t, so written by having ampersand mark in front of T. So this is a type representing a reference to T. But more specifically, it is a borrowing pointer, a borrowing reference, not an owning pointer. And by default, it is an immutable pointer, which means that you cannot modify the data type T, the underlying data, through this reference. But this is whether the most basic way you can make a borrowing pointer to a data structure, so called ref_t. And the second one, ref_mut_t. So mut represents mutable. So if you want to make some modification to the underlying data structure of data type T, then you should make this ref_mut reference. So it is a mutable borrowing pointer to data of type T. So the third one is the owning pointer. So you make a box of T. So you call it box T. So this represents an owning pointer to T. So these three are basics, and the most important ones are the 1 and 3. So the distinction between the first and second is somewhat orthogonal to the memory management stuff. So ref_t is the borrowing pointer. Box T is the owning pointer. So these are two basics every one of you have to remember. And 4 and 5 are what I mentioned as some workarounds to these two basics. So RC or ARC are something called shared pointer, but essentially these are reference counting pointers. So this could be used when you like to have multiple pointers owning to the particular data structure anyways. And this asterisk star T is an unsafe pointer, when it's just reminiscent of C's pointer syntactically. So following discussions are almost totally focused on these three things. So ref_t and box_t, and occasionally ref_mut_t. So I'm going to talk much about these reference counting and unsafe pointers that are not interesting part of the Rust memory management system. So this is the illustration of the same thing. So earlier I conceptually talked about owning pointer and borrowing pointers, but to be more specific in the Rust context, So there's one box T pointing to T, and there can be any number of ref T's, right? Or perhaps a ref mute T. So this is the pointer-like data types. So these are all types in Rust. And just like you have some ways to represent pointer-like types in Rust, there should be, and there are indeed, some expressions with which you can make pointer-like data. So this is how you can do that in Rust. So let's say you are given an expression E of type T. So below are expressions that make pointer-like data to the value of E. So one way is just like you did when you make a type. You can also have this ampersand right before any expression, which makes an expression of type ref T, obviously. And this makes an immutable borrowing pointer, as you can already guess. But you cannot modify the underlying data through this pointer. So this is an expression that makes immutable borrowing pointer to the value of this expression. And as you can easily imagine, you have an expression written as ref mute any expression, which makes an expression of type ref mute T, not surprisingly. And this makes a mutable borrowing pointer, so through which you can modify the data referenced by this entire expression. And this is the way you can make owning pointer. So box new of E. So this makes an expression of type box T. Well, obviously, this makes an owning pointer to the value of this expression. So these are mostly for setting the context. So nothing is profoundly difficult so far. So just to make sure we are on the same page. So here is an example. So a concrete Rust program fragment that uses all these concepts. So first of all, you make a structure, let's say S, and you assign the structure to a variable A. And you can make a reference to this structure by ref A. So this is an expression that makes a reference. And you can assign the reference to a variable of type ref S. Because A is S, reference to S is reference to S. So sorry, so because A is of type S, then reference to A is of type reference to S. And also you can make a mutable borrowing reference by ref mute A and assign it to a variable of type ref mute S. And you can also make an owning pointer by box new A. And you can assign it to a variable of box S, right? So these are, well, exactly the three ways I have just introduced to make pointer-like data in Rust. And one small note is that these type declarations right after variable declarations, variable names, can be omitted because they can easily be inferred from the right-hand side. But in this example, I just spelled out for clarity, just to clarify how types can be spelled out. And another note is, well, this piece of program actually doesn't compile for the reasons I have not talked about yet. So I'm going to get into them. So the above program already violates some rules that are enforced by Rust. So I'll get to that later. So these are sort of context. So you have holding pointer, box T, borrowing pointer, ref T, right? And so let me get gradually into the exact rules enforced by Rust and how you can write a program that obeys these rules. So first rule, somewhat surprising, that is enforced by Rust is this: assignments move the value. So this is somewhat different from what you have in ordinary or most other programming languages. So in most, if not all, programming languages, assignments basically copy the value in the variable. But in the case of Rust, it moves the value. This is necessary to maintain the restriction that there can be only one owning pointer. So to maintain that there is only one owning pointer, an assignment in Rust moves the value out of the right-hand side. And this allows further use of it. So when you have an assignment like this, x equal y, what happens is that y can no longer be used after this assignment. Well, just to explain why this rule is necessary, or at least reasonable to have, if you like to enforce this single owning pointer rule. So let me use this example. So first of all, you have a data structure of type S, and you have a variable having a reference to this data structure. Well, not surprisingly, you can use, for example, a.x or a.y in these places. But let's say you have another variable and assign a to the new variable, like b called a. Then what happens in Rust, unlike other programming languages, is this. So rather than having both A and B pointing to the same object, A no longer points to the this data structure. So only B now points to this data structure. So what specifically happens when you go on with something like this is, for a.x, the Rust compiler complains. So this program cannot be compiled. b.x is okay. So after this assignment, the same data structure can be referenced or used only through this b variable, not from a. And conceptually, this is what is happening here. So after this assignment, the pointer inside this a variable goes away, and the pointer moves to the new variable b. This is the conceptual, so the model you should have in your mind when you reason about the behavior of assignment in Rust. And a similar thing happens elsewhere. So anywhere you have something like an assignment. So not literally the exact assignment statement. For example, a similar thing happens when you pass arguments to functions. So passing a value to a function also moves the value out. So the example is exactly the same as before so far. So in these 3 lines. But let's say you have a function call passing this variable a to another function f. So again, here again, so we like to maintain the single owning pointer rule, right? So when you do something like this, the single owning pointer should be the parameter of this function f, right? So if we also maintain a pointing to the original object, then you end up with having 2 pointers pointing to it, which violates the last rule, right? So as such, a dot x after you call f of a is prohibited. So this is something the Rust compiler complains about. So just to illustrate what actually happens, so you can think of the program originally having a pointing to this variable, but when you call f of f of x, then the pointer in the original variable a will go away, and the pointer is now held in the variable of f's parameter. So I guess this somewhat surprises you. So and maybe so if you are already doing some programming in Rust, this might surprise you and perhaps confuse you, because this behavior may not be what you have been witnessing in the past Rust programming experiments. So actually, so what I have mentioned, the value moving assignment, not value copying assignment, may contradict what you have seen in your experiences in Rust programming. Well, specifically, does it apply to all types, including very primitive types like floating point numbers? So if this equally applies to all types, including primitive types like floating point numbers and integers, this program is already violating the Rust rule. So let's say you have a floating point number and a variable of floating point number a. You assign a to another variable b. Then according to the rule I have mentioned, you shouldn't be able to use a anymore after this assignment. Is it really the rule you have been programming the Rust with? Well, actually, it's not quite. So there are some exceptions. I'm not sure whether I should call them exceptions, but there are ways these assignments should be treated somewhat differently. So to straightforwardly answer to the question about this program, then well, in this particular case, no. So it does not apply to primitive types like these things. So this program is totally valid. So there's actually a more general answer to this question. So actually, this value moving assignment rule does not apply to data types that implement something called copy trait. So you can actually make a structure whose assignment behave like primitive types, like integers or floating point numbers. This can be simply be done by having this somewhat mystic clause in front of your structure definition. So when you have this clause in front of structure definition, then value assignment behaves somewhat differently. So the way it behaves is something like this. So when you do some variable assignment like V equal A, then A points to the original data structure, and B now points to the copy of it. So the assignment makes a copy of the data structure it points to. Right? So it should be different from, well, so you shouldn't be confused with copying a pointer to it. So having two pointers pointing to the same data structure. This is not what happens here. So you make a copy of the data structure itself, and A points to one and B points to the other. Now, so both A.x and B.x are okay. So you can do both. So one notable thing about this is that this doesn't violate single owner rule, single owning pointer rule, right? So each variable points to a different data structure. So each object still has only one owning pointer. So this single owner rule is still somewhat trivially maintained. So in the following, we will only discuss types not implementing copy trait. So as a matter of fact, so when every assignment makes the copy of the data structure it points to, then well, actually memory management is almost trivial, right? So when a variable goes away, the associated data structure can be reclaimed safely because there are no pointers pointing to it, right? So the memory management is difficult when there may be some other references to it, right? So when you lose a variable pointing to a data structure, you are not sure whether it's safe to reclaim the object I'm pointing to with this variable or not, because you do not necessarily know how many other pointers may still be pointing to it. So if every time you do an assignment, you make a copy of the data structure, then memory management is trivial, nothing difficult. So down the road, I'm going to focus on data structures that do not implement copy traits. So this is the one important basic about Rust. And the next topic is this owning pointer box T. So like I said already, box T is a type representing an owning pointer to data T. And you can make an owning pointer by this expression, box new, whatever value you want to point to. So just like other ordinary function call, this is actually moving the value out of V. So this entire expression becomes the new owning pointer. So let me illustrate this by a similar example. So like before, I make a structure of type S, and A points to A. And we now make a owning pointer or box A by this expression. So actually a very similar thing happens as before. So all variable now points to the original data structure created here. But A can no longer reference to it. But this is actually the same rule applied to what happens when you pass a variable to a function, right? Simply because you are passing A to a function, you can no longer difference this data structure through A. So again, A dot X is not allowed, but O dot X is allowed. So this is actually somewhat verbose, but formal syntax. So when you have box of something, you say star whatever to refer to the underlying data structure. And you get the underlying data structure, this data structure, and say dot X to get the value you stored here. But actually, just for your convenience, Rust allows you to write something like this, O dot X, simply O dot X, without having this star. But this could be, this is somewhat more formal, but this is an abbreviation of this one. But these differences are not very important here. But box makes a owning pointer. So these two concepts are somewhat similar to what you have in C or C++. So you may, at least apparently you may be thinking that the box new is somewhat like a malloc, and ordinary structure allocation is somewhat similar to allocating a struct variable as a local variable. But albeit these somewhat syntactic similarities, there are no, well, so these two things are different, at least very different. So you shouldn't be confused. And you shouldn't try to make too strong analogies between them. So Rust data structure lives as long as there's an owning pointer to it. So for example, you make a structure here, and this structure lives as long as this variable, because A is the owning pointer to this data structure. And A goes out of scope at this point. So this is where A dies, right? So as a consequence, S will also die here. So the data structure dies at the very moment that its owning pointer dies. This happens no matter whether you have a pointer. Oh, so sorry, I was wrong. So S will die here because its owning pointer P. So now the owning pointer is P, right? Owning pointer P dies here, right? So if you make a too strong analogy between Rust and C or C++, you may consider this just somewhat like a malloc or heap allocation. So it lives indefinitely. So this is wrong. So this is not what happens in Rust. So Rust knows that P is the owning pointer, and when the owning pointer or any pointer of box T goes out of scope, which happens here, then the object it points to should die at the same time. So this is how Rust manages memory. So well, exactly the same thing happens when you do not use box at all. So if you simply say let P equal E, so without making a explicit box, exactly the same thing happens. So after this P equal A assignment, P becomes the owning pointer of this data structure. And simply because P goes out of scope at this point, this data structure will be reclaimed when P goes out of scope. So well, in a way, these two programs do not make any significant difference. So after having heard of this, you may be somewhat confused. So what is then the purpose of this box T at all? So just like the previous example indicates, so the behavior or the lifetime of this data structure is exactly the same no matter whether you have this box or not. Well, as a matter of fact, you may think of P another owning pointer, right? So both in both of these programs, P is the owning pointer of this data structure after this assignment. So you might naturally wonder what is the difference between a box of T and T itself? Well, this is a very legitimate question. So just to state once again somewhat more clearly, so for any value V of type T, so you can have one and only one variable that refers to V, which is either of type T or box T. So you may have a variable of type T, or you may have a variable of box T, but not both. Likewise, you may not have, you cannot have two variables both type T or two variables both box T differencing the same data structure. Well, in that sense, T and box T are quite similar. So you can think of T as just another kind of pointer to T, just like a box T. So there's no fundamental distinction between T and box T. So is there any reason for why the last has both T and box T? Well, actually, in my understanding, the only case in which the distinction becomes semantically significant is when you have recursive types, recursive data types. So the distinction becomes important when you reason about data layout of structures. So basically, Rust says that when you have a field of type T in another struct S, it says it embeds this data of T into S. So for example, if T is a structure having, for example, 1,000 bytes, then S becomes, well, at least as large as T2. It's somewhat different from other languages in which T, in implementation terms, T always is a reference to T. So this happens in Java. But the Rust is somewhat different. So when you write T in S and when you write box T in U, data layouts are actually different. So if you have a T as large as 1,000 bytes, then S is as large as T, but a U is not. Well, so the P field in U is just a pointer, well, probably 64 bits or something like that. So the distinction becomes important only in these cases. And in terms of the data's lifetime, these two makes no difference. So in both cases, if the containing structure goes away, then the data pointed to by P will also go away because this is the only pointer pointing to it, the owning pointer pointing to it. So no matter whether it's box or T. So in terms of the memory management perspective, these two are not very different. But when you reason about the data layout of the structure, these two make a difference. And the situation in which this becomes particularly important is when you have recursive data types, where struct S having a field of another struct S. This is not allowed. Well, this is well, so you cannot think of a reasonable implementation for this, right? So if S is embedded in the containing data structure, you cannot make a reasonable data layout for this structure, right? So the only way to get around this is in implementation terms, make this a pointer to itself. So this is valid and legitimate. So in these cases, the distinction between T and box T become significant. But otherwise, yeah, these two things are fairly interchangeable at least in Rust. And in particular, the distinction is not very important when discussing lifetime. So how memory is managed in Rust. Okay. So far I have been talking about owning pointers, and there are a few more things I want to talk about owning pointers, but well, I cannot finish the entire slide anyway for today. So let's leave the remaining things in the next week, and so let's have time to work on these exercises. So before getting into exercises, do you have any question?